Scuba diving is a form of underwater diving in which a diver uses a self-contained underwater breathing apparatus to breathe underwater. Unlike other modes of diving, which rely either on breath hold or on air pumped from the surface, scuba divers carry their own source of breathing gas, allowing them greater freedom of movement than with an airline or diver's umbilical and longer underwater endurance than breath hold. Scuba equipment may be open circuit, in which exhaled gas is expelled to the surroundings, or a closed or semi-closed circuit rebreather, in which the breathing gas is scrubbed to remove carbon dioxide, and the oxygen used is replenished from a supply of feed gas before being rebreathed. A scuba diver usually moves around underwater by using fins attached to the feet, but external propulsion can be provided by a diver propulsion vehicle, or a sled pulled from the surface. History. By the early 20th century, two basic templates for scuba had emerged. Open-circuit scuba, where the diver's exhaust is vented directly into the water, and closed-circuit scuba, where the diver's unused oxygen is filtered from the carbon dioxide and recirculated. Rebreathers. The closed-circuit rebreathers were first developed for military use, due to their stealth advantages. The first commercially successful closed-circuit scuba was designed and built by English diving engineer, Henry Flees, in 1878, while working for Sebe Gorman in London. His self-contained breathing apparatus consisted of a rubber mask connected to a breathing bag, with 50 to 60% O2 supplied from a copper tank and CO2 scrubbed by rope yarn soaked in a solution of caustic potash. The system giving a duration of about 3 hours. Sir Robert Davis, head of Sebe Gorman, perfected the Oxygen Rebreather in 1910 with his invention of the Davis submerged escape apparatus, the first practical rebreather to be made in quantity. Rebreathers have been increasingly used by civilians for recreation, especially since the end of Cold War. This reduced the perceived risk of attack by communist bloc forces, including by their combat divers. After that, the world's armed forces had less reason to requisition civilian rebreather patents, and automatic and semi-automatic recreational diving rebreathers started to appear. Open-circuit scuba. The first commercially successful scuba sets were the Aqualung twin-hose open-circuit units developed by Emile Gagnon and Jacques-Yves Cousteau, in which compressed air carried in back-mounted cylinders is inhaled through a demand regulator and then exhaled into the water adjacent to the tank. The single-hose two-stage scuba regulators trace their origins to Australia, where Ted Eldred developed the first example of this type of regulator, known as porpoise scuba gear. This was developed because patents protected the Aqualung's twin-hose design. The single-hose regulator separates the cylinder from the demand valve, giving the diver air at the pressure at their mouth, not that at the top of the cylinder. Etymology. The term scuba originally referred to United States combat frogmen's oxygen rebreathers, developed during World War II by Christian J. Lambertson for underwater warfare. Scuba was originally an acronym, but is now generally used as a common noun or adjective, scuba. It has become acceptable to refer to scuba equipment, or scuba apparatus. Examples of the linguistic RAS syndrome. Applications of scuba diving. Scuba diving may be performed for a number of reasons, both personal and professional. Recreational diving is performed purely for enjoyment and has a number of distinct technical disciplines to increase interest underwater, such as cave diving, wreck diving, ice diving and deep diving. Divers may be employed professionally to perform tasks underwater. Some of these tasks are suitable for scuba. Professional scuba divers are trained to manage situations in which they may face vertigo or entanglement. There are divers who work, full or part-time, in the recreational diving community as instructors, assistant instructors, dive masters and dive guides. In some jurisdictions the professional nature, with particular reference to responsibility for health and safety of the clients, of recreational diver instruction, dive leadership for reward and dive guiding is recognized and regulated by national legislation. Other specialist areas of scuba diving include military diving, with a long history of military frogmen in various roles. They can perform roles including direct combat, infiltration behind enemy lines, placing mines or using a manned torpedo, bomb disposal or engineering operations. In civilian operations, Many police forces operate police diving teams to perform search and recovery, or search and rescue operations and to assist with the detection of crime which may involve bodies of water. In some cases diver rescue teams may also be part of a fire department, paramedical service or lifeguard unit, and may be classed as public service diving. Lastly, there are professional divers involved with the water itself, such as underwater photography or underwater videography divers, who document the underwater world, or scientific diving, including marine biology, geology, hydrology, oceanography and underwater archaeology. The choice between scuba and surface-supplied diving equipment is based on both legal and logistical constraints. Where the diver requires mobility and a large range of movement, scuba is usually the choice if safety and legal constraints allow. Higher-risk work, particularly in commercial diving, may be restricted to surface-supplied equipment by legislation and codes of practice. Diving activities commonly associated with scuba include depth range. The depth range applicable to scuba diving depends on the application and training, but most dives are shallower than 30 m. Recreational diving limits decompression to no-stop dives or relatively short planned decompression stops to minimize risk of decompression sickness. Recreational scuba is generally limited to between 30 and 40 m, depending on the certifying agency. Professional diving also limits the allowed planned decompression depending on the code of practice, operational directives or statutory restrictions which apply. Depth limits depend on the jurisdiction, and maximum depths allowed range from 30 m to more than 50 m, depending on the breathing gas used and the availability of a decompression chamber on site. Technical diving may involve exploring the logistical and physiological limits, and in these cases a higher risk is accepted by the diver, and considerable effort may be made to reduce this risk by careful planning and contingency procedures. Depths are limited by physiological and logistical aspects, the amount of gas that can be carried, decompression requirements, gas toxicity at high pressure and work of breathing constraints. Equipment. Breathing apparatus. The defining equipment used by a scuba diver is the eponymous scuba, the self-contained underwater breathing apparatus which allows the diver to breathe while diving, and is transported by the diver. As one descends, in addition to the normal atmospheric pressure, the water exerts increasing hydrostatic pressure of approximately 1 bar for every 10 m of depth. The pressure of the inhaled breath must balance the surrounding or ambient pressure to allow inflation of the lungs. It becomes virtually impossible to breathe air at normal atmospheric pressure through a tube below 3 feet under the water. Most recreational scuba diving is done using a half mask which covers the diver's eyes and nose, and a mouthpiece to supply the breathing gas from the demand valve or rebreather. Inhaling from a regulator's mouthpiece becomes second nature very quickly. The other common arrangement is a full-face mask which covers the eyes, nose and mouth, and often allows the diver to breathe through the nose. Professional scuba divers are more likely to use full-face masks. Open circuit. Open circuit scuba has no provision for using the breathing gas more than once for respiration. The gas inhaled from the scuba equipment is exhaled to the environment, or occasionally into another item of equipment for a special purpose, usually to increase buoyancy of a lifting device such as a buoyancy compensator, inflatable surface marker buoy or small lifting bag. The breathing gas is generally provided from a high-pressure diving cylinder through a scuba regulator. By always providing the appropriate breathing gas at ambient pressure, demand valve regulators ensure the diver can inhale and exhale naturally and without excessive effort, regardless of depth, as and when needed. The most commonly used scuba set uses a single-hose open-circuit two-stage demand regulator, connected to a single back-mounted high-pressure gas cylinder, with the first stage connected to the cylinder valve and the second stage at the mouthpiece. This arrangement differs from Emile Gagnon's and Jacques Cousteau's original 1942 twin-hose design, known as the Aqualung, in which the cylinder pressure was reduced to ambient pressure in one or two stages which were all in the housing mounted to the cylinder valve or manifold. The single-hose system has significant advantages over the original system for most applications. In the single-hose two-stage design, The first stage regulator reduces the cylinder pressure of up to about 300 bar to an intermediate level of about 10 bar above ambient pressure. The second stage demand valve regulator, supplied by a low-pressure hose from the first stage, delivers the breathing gas at ambient pressure to the diver's mouth. The exhaled gases are exhausted directly to the environment as waste. The first stage typically has at least one outlet port delivering breathing gas at full tank pressure, which is connected to the diver's submersible pressure gauge or dive computer, to show how much breathing gas remains in the cylinder. Rebreather. Less common are closed-circuit and semi-closed rebreathers, which unlike open-circuit sets that vent off all exhaled gases, process all or part of each exhaled breath for reuse by removing the carbon dioxide and replacing the oxygen used by the diver. Rebreathers release little or no gas bubbles into the water, and use much less stored gas volume, for an equivalent depth and time because exhaled oxygen is recovered. This has advantages for research, military, photography, and other applications. Rebreathers are more complex and more expensive than open-circuit scuba, and special training and correct maintenance are required for them to be safely used, due to the larger variety of potential failure modes. In a closed-circuit rebreather, the oxygen partial pressure in the rebreather is controlled, so it can be maintained at a safe continuous maximum, which reduces the inert gas partial pressure in the breathing loop. Minimizing the inert gas loading of the diver's tissues for a given dive profile reduces the decompression obligation. This requires continuous monitoring of actual partial pressures with time, and for maximum effectiveness requires real-time computer processing by the diver's decompression computer. Decompression can be much reduced compared to fixed-ratio gas mixers used in other scuba systems and, as a result, divers can stay down longer or require less time to decompress. A semi-closed circuit rebreather injects a constant mass flow of a fixed breathing gas mixture into the breathing loop, or replaces a specific percentage of the respired volume, so the partial pressure of oxygen at any time during the dive depends on the diver's oxygen consumption and/or breathing rate. Planning decompression requirements requires a more conservative approach for a SCR than for a CCR, but decompression computers with a real-time oxygen partial pressure input can optimize decompression for these systems. Because rebreathers produce very few bubbles, they do not disturb marine life or make a diver a unregistered trademark as presence known at the surface. This is useful for underwater photography, and for covert work. Gas mixtures. For some diving, gas mixtures other than normal atmospheric air can be used, so long as the diver is competent in their use. The most commonly used mixture is nitrox, also referred to as enriched air nitrox, which is air with extra oxygen, often with 32% or 36% oxygen, and thus less nitrogen, reducing the risk of decompression sickness or allowing longer exposure to the same pressure for equal risk. The reduced nitrogen may also allow for no stops or shorter decompression stop times or a shorter surface interval between dives. A common misconception is that nitrox can reduce narcosis, but research has shown that oxygen is also narcotic. The increased partial pressure of oxygen due to the higher oxygen content of nitrox increases the risk of oxygen toxicity, which becomes unacceptable below the maximum operating depth of the mixture. To displace nitrogen without the increased oxygen concentration, other diluent gases can be used, usually helium, when the resultant three-gas mixture is called trimix, and when the nitrogen is fully substituted by helium, holiox. For dives requiring long decompression stops, divers may carry cylinders containing different gas mixtures for the various phases of the dive, typically designated as travel, bottom, and decompression gases. These different gas mixtures may be used to extend bottom time, reduce inert gas narcotic effects, and reduce decompression times. Diver mobility. To take advantage of the freedom of movement afforded by scuba equipment, the diver needs to be mobile underwater. Diver propulsion. Personal mobility is enhanced by fins and optionally diver propulsion vehicles. Fins have a large blade area and use the more powerful leg muscles, so are much more efficient for propulsion and maneuvering thrust than arm and hand movements, but require skill to provide fine control. Streamlining dive gear will reduce drag and improve mobility. Balance trim, which allows the diver to align in any desired direction, also improves streamlining by presenting the smallest section area to the direction of movement and allows propulsion thrust to be used more efficiently. Occasionally a diver may be towed using a sled, an unpowered device towed behind a surface vessel, which conserves the diver's energy and allows more distance to be covered for a given air consumption and bottom time. The depth is usually controlled by the diver by using diving planes or by tilting the whole sled. Some sleds are faired to reduce drag on the diver. Buoyancy control. To dive safely, divers must control their rate of descent and ascent in the water and be able to maintain a constant depth in midwater. Ignoring other forces such as water currents and swimming, the diver's overall buoyancy determines whether they ascend or descend. Equipment such as diving weighting systems, diving suits and buoyancy compensators can be used to adjust the overall buoyancy. When divers want to remain at constant depth, they try to achieve neutral buoyancy. This minimizes the effort of swimming to maintain depth and therefore reduces gas consumption. The buoyancy force on the diver is the weight of the volume of the liquid that they and their equipment displace minus the weight of the diver and their equipment. If the result is positive, that force is upwards. The buoyancy of any object immersed in water is also affected by the density of the water. The density of fresh water is about 3% less than that of ocean water. Therefore, divers who are neutrally buoyant at one dive destination will predictably be positively or negatively buoyant when using the same equipment at destinations with different water densities. The removal of diver weighting systems can be used to reduce the diver's weight and cause a buoyant ascent in an emergency. Diving suits made of compressible materials decrease in volume as the diver descends, and expand again as the diver ascends, causing buoyancy changes. Diving in different environments also necessitates adjustments in the amount of weight carried to achieve neutral buoyancy. The diver can inject air into dry suits to counteract the compression effect and squeeze. Buoyancy compensators allow easy and fine adjustments in the diver's overall volume and therefore buoyancy. For open-circuit divers, changes in the diver's average lung volume during a breathing cycle can be used to make fine adjustments of buoyancy. Neutral buoyancy in a diver is an unstable state. It is changed by small differences in ambient pressure caused by a change in depth, and the change has a positive feedback effect. A small descent will increase the pressure, which will compress the gas-filled spaces and reduce the total volume of diver and equipment. This will further reduce the buoyancy, and unless counteracted, will result in sinking more rapidly. The equivalent effect applies to a small ascent, which will trigger an increased buoyancy and will result in accelerated ascent unless counteracted. The diver must continuously adjust buoyancy or depth in order to remain neutral. This is a skill which improves with practice until it becomes second nature. Buoyancy changes with depth variation are proportional to the compressible part of the volume of the diver and equipment, and to the proportional change in pressure, which is greater per unit of depth near the surface. Minimizing the volume of gas required in the buoyancy compensator will minimize the buoyancy fluctuations with changes in depth. This can be achieved by accurate selection of ballast weight, which should be the minimum to allow neutral buoyancy with depleted gas supplies at the end of the dive unless there is an operational requirement for greater negative buoyancy during the dive. Buoyancy and trim can significantly affect drag of a diver. The effect of swimming with a head-up angle, of about 15 degrees is quite common in poorly trimmed divers, can be an increase in drag in the order of 50%. Underwater vision. Water has a higher refractive index than air, similar to that of the cornea of the eye. Light entering the cornea from water is hardly refracted at all, leaving only the eye's crystalline lens to focus light. This leads to very severe hypermetropia. People with severe myopia, therefore, can see better underwater without a mask than normal-sighted people. Diving masks. Diving masks and helmets solve this problem by providing an airspace in front of the diver's eyes. The refraction error created by the water is mostly corrected as the light travels from water to air through a flat lens, except that objects appear approximately 34% bigger and 25% closer in water than they actually are. Therefore total field of view is significantly reduced and eye-hand coordination must be adjusted. This also affects underwater photography. A camera seeing through a flat port in its housing is affected in the same way as its user's eye seeing through a flat mask viewport, and so its operator must focus for the apparent distance to target, not for the real distance. This is only relevant for manual focusing. Divers who need corrective lenses to see clearly outside the water would normally need the same prescription while wearing a mask. Generic and custom corrective lenses are available for some two-window masks. Custom lenses can be bonded onto masks that have a single front window or two windows. A double-dome ported mask has curved viewports in an attempt to cure these faults, but this causes a refraction problem of its own. Cylindrically curved faceplates such as those used for firefighting full-face masks produce severely distorted views underwater. Commando frogmen concerned about revealing their position when light reflects from the glass surface of their diving masks may instead use special contact lenses to see underwater. As a diver descends, they must periodically exhale through their nose to equalize the internal pressure of the mask with that of the surrounding water. Swimming goggles are not suitable for diving because they only cover the eyes and thus do not allow for equalization. Failure to equalize the pressure inside the mask may lead to a form of barotrauma known as mask squeeze. Dive lights. Water attenuates light by selective absorption. Pure water preferentially absorbs red light, and to a lesser extent, yellow and green, so the color that is least absorbed is blue light. Dissolved materials may also selectively absorb color in addition to the absorption by the water itself. In other words, as a diver goes deeper on a dive, more color is absorbed by the water, and in clean water the color becomes blue with depth. Color vision is also affected by turbidity of the water, which tends to reduce contrast. Artificial light is useful to provide light in the darkness, and to restore natural color lost to absorption. Environmental protection. Protection from heat loss in cold water is usually provided by wetsuits or dry suits. These also provide protection from sunburn, abrasion and stings from some marine organisms. Where thermal insulation is not important, lycra suits' diving skins may be sufficient. Wetsuits. A wetsuit is a garment, usually made of foamed neoprene, which provides thermal insulation, abrasion resistance and buoyancy. The insulation properties depend on bubbles of gas enclosed within the material, which reduce its ability to conduct heat. The bubbles also give the wetsuit a low density, providing buoyancy in water. A good close fit and few zips helps the suit to remain waterproof and reduce flushing, the replacement of water trapped between suit and body by cold water from the outside. Improved seals at the neck, wrists and ankles and baffles under the entry zip produce a suit known as a semi-dry. Suits range from a thin shorty, covering just the torso, to a full 8-ounce semi-dry, usually complemented by neoprene boots, gloves and hood. Dry suits. A dry suit provides thermal insulation to the wearer while immersed in water, and normally protects the whole body except the head, hands, and sometimes the feet. In some configurations, these are also covered. Dry suits are usually used where the water temperature is below 15 degrees Celsius or for extended immersion in water above 15 degrees Celsius, where a wetsuit user would get cold, and with an integral helmet, boots, and gloves for personal protection when diving in contaminated water. Dry suits are designed to prevent water entering. This generally allows better insulation, making them more suitable for use in cold water. They can be uncomfortably hot in warm or hot air, and are typically more expensive and more complex to don. For divers, they add some degree of complexity as the suit must be inflated and deflated with changes in depth in order to avoid squeeze on descent or uncontrolled rapid ascent due to overbuoyancy. Monitoring and navigation. Unless the maximum depth of the water is known, and is quite shallow, a diver must monitor the depth and duration of a dive to avoid decompression sickness. Traditionally this was done by using a depth gauge and a diving watch, but electronic dive computers are now in general use, as they are programmed to do real-time modeling of decompression requirements for the dive, and automatically allow for surface interval. Many can be set for the gas mixture to be used on the dive, and some can accept changes in the gas mix during the dive. Most dive computers provide a fairly conservative decompression model, and the level of conservatism may be selected by the user within limits. Most decompression computers can also be set for altitude compensation to some degree. If the dive site and dive plan require the diver to navigate, a compass may be carried, and where retracing a route is critical, as in cave or wreck penetrations, a guideline is laid from a dive reel. In less critical conditions, many divers simply navigate by landmarks and memory, a procedure also known as pilotage or natural navigation. A scuba diver should always be aware of the remaining breathing gas supply, and this is usually monitored by using a submersible pressure gauge on each cylinder. Safety equipment. Cutting tools such as knives, line cutters or shears are often carried by divers to cut loose from entanglement in nets or lines. A surface marker buoy on a line held by the diver indicates the position of the diver to the surface personnel. This may be an inflatable marker deployed by the diver at the end of the dive, or a sealed float, towed for the whole dive. A surface marker also allows easy and accurate control of ascent rate and stop depth for safer decompression. Various surface detection aids may be carried to help surface personnel spot the diver after ascent. Accessories. Divers may carry underwater photographic or video equipment, or tools for a specific application in addition to diving equipment. Procedures. The underwater environment is unfamiliar and hazardous, and a large part of safe diving involves the following of procedures which are simple but necessary to ensure the safety of the divers. A certain minimum level of attention to detail and acceptance of responsibility for one's own safety and survival are required. Most of the procedures are simple and straightforward, and become second nature to the experienced diver, but must be learned, and take some practice to become automatic and faultless, just like the ability to walk or talk. Most of the safety procedures are intended to reduce the risk of drowning, and many of the rest are to reduce the risk of barotrauma and decompression sickness. In some applications, getting lost is a serious hazard, and specific procedures to minimize the risk are followed. Preparation for the dive. Preparation for a dive includes equipment checks to ensure that the correct equipment is available and in good working order, dive planning to ensure that the divers do not exceed their comfort zone or skill level, or the safe capacity of their equipment, and scuba gas planning to ensure that the amount of breathing gas to be carried is sufficient to allow for any reasonably foreseeable contingencies. Standard diving procedures. Water entry and descent procedures are carried out first to enter the water without injury or loss of damage to equipment. These procedures also cover how to descend at the right place, time, and rate, with the correct breathing gas available, and without losing contact with the other divers in the group. Equalization of pressure in gas spaces to avoid barotraumas of descent. Ear clearing is one of the more critical equalization procedures, usually requiring conscious intervention by the diver. Mask and regulator clearing may be needed to ensure ability to see and breathe in case of flooding. This can easily happen and is not considered an emergency. Buoyancy control and diver trim require frequent adjustment to ensure safe and convenient underwater mobility during the dive. Buddy checks, breathing gas monitoring, and decompression status monitoring are carried out to ensure that the dive plan is followed and that members of the group are safe available to help each other in an emergency. Ascent, decompression, and surfacing, to ensure that dissolved gases are safely released, that barotraumas of ascent are avoided, and that it is safe to surface. Water exit procedures, to leave the water again without injury or loss of damage to equipment. Post-dive procedures. These include debriefing where appropriate, and equipment maintenance, to ensure that the equipment is kept in good condition for later use. Buddy, team or solo diving. Buddy and team diving procedures are intended to ensure that a recreational scuba diver who gets into difficulty underwater is in the presence of a similarly equipped person who can render assistance. Divers are trained to assist in those emergencies specified in the training standards for their certification, and may be required to demonstrate competence in the prescribed skills. Solo divers take the responsibility for their own safety and compensate for the absence of a buddy by skill, vigilance and appropriate equipment. Underwater communication. A diver cannot talk underwater unless he is wearing a full face mask and electronic communications equipment, but divers can communicate basic and emergency information using hand signals, light signals, and rope signals, and more complex messages can be written on waterproof slates. Emergency procedures. The most urgent emergencies specific to scuba diving generally involve loss of breathing gas, gas supply failures, situations where breathing air is likely to run out before the diver can surface, or inability to ascend, and uncontrolled ascents. Emergency ascents. Controlled emergency ascents are almost always a consequence of loss of breathing gas, while uncontrolled ascents are usually the result of a buoyancy control failure. Emergency air sharing. The most urgent underwater emergencies usually involve a compromised breathing gas supply. Divers are trained in procedures for donating and receiving breathing gas from each other in an emergency, and may carry an alternative air source if they do not choose to rely on a buddy. Rescue of an unresponsive diver. Divers may be trained in procedures which have been approved by the training agencies for recovery of an unresponsive diver to the surface, where it might be possible to administer first aid. Not all recreational divers have this training, as some agencies do not include it in entry-level training. Professional divers may be required by legislation or code of practice to have a standby diver at any diving operation, who is both competent and available to attempt rescue of a distressed diver. Entrapment. Two basic types of entrapment are significant hazards for scuba divers: inability to navigate out of an enclosed space, and physical entrapment, which prevents the diver from leaving a location. The first case can usually be avoided by staying out of enclosed spaces, and when the objective of the dive includes penetration of enclosed spaces, taking precautions such as the use of lights and guidelines. The most common form of physical entrapment is getting snagged on ropes, lines or nets, and use of a cutting implement is the standard method of dealing with the problem. The risk of entanglement can be reduced by careful configuration of equipment to minimize those parts which can easily be snagged, and allow easier disentanglement. Other forms of entrapment, such as getting wedged into tight spaces, can often be avoided, but must otherwise be dealt with as they happen. The assistance of a buddy may be helpful where possible. Emergency procedures for specific scuba applications. Scuba diving in relatively hazardous environments such as caves and wrecks, areas of strong water movement, relatively great depths, with decompression obligations, with equipment that has more complex failure modes, and with gases that are not safe to breathe at all depths of the dive require specialized safety and emergency procedures tailored to the specific hazards. Hazards of scuba diving. According to a 1970 North American study, diving was 96 times more dangerous than driving an automobile. According to a 2000 Japanese study, every hour of recreational diving is 36 to 62 times riskier than automobile driving. A big difference between the risks of driving and diving is that the diver is less at risk from fellow divers than the driver is from other drivers. Injuries due to changes in pressure. Divers must avoid injuries caused by changes in pressure. The weight of the water column above the diver causes an increase in pressure in proportion to depth, in the same way that the weight of the column of atmospheric air above the surface causes a pressure of 101.3 kPa at sea level. This variation of pressure with depth will cause compressible materials and gas-filled spaces to tend to change volume, which can cause the surrounding material or tissues to be stressed, with a risk of injury if the stress gets too high. Pressure injuries are called barotrauma and can be quite painful, even potentially fatal in severe cases causing a ruptured lung, eardrum or damage to the sinuses. To avoid barotrauma, the diver equalizes the pressure in all air spaces with the surrounding water pressure when changing depth. The middle ear and sinus are equalized using one or more of several techniques, which is referred to as clearing the ears. The scuba mask is equalized during descent by periodically exhaling through the nose. During ascent it will automatically equalize by leaking excess air around the edges. A helmet or full-face mask will automatically equalize, as any pressure differential will either vent through the exhaust valve or open the demand valve and release air into the low-pressure space. If a dry suit is worn, it must be equalized by inflation and deflation, much like a buoyancy compensator. Most dry suits are fitted with an auto-dump valve, which, if set correctly, and kept at the high point of the diver by good trim skills, will automatically release gas as it expands and retain a virtually constant volume during ascent. During descent the dry suit must be inflated manually. Although there are many dangers involved in scuba diving, divers can decrease the risks through proper procedures and appropriate equipment. The requisite skills are required by training and education, and honed by practice. Open water certification programs highlight diving physiology, safe diving practices, and diving hazards, but do not provide the diver with sufficient practice to become truly adept. Effects of breathing high-pressure gas. Decompression sickness. The prolonged exposure to breathing gases at high partial pressure will result in increased amounts of non-metabolic gases, usually nitrogen and/or helium, dissolving in the bloodstream as it passes through the alveolar capillaries, and thence carried to the other tissues of the body, where they will accumulate until saturated. This saturation process has very little immediate effect on the diver. However, when the pressure is reduced during ascent, the amount of dissolved inert gas that can be held in stable solution in the tissues is reduced. This effect is described by Henry's law. As a consequence of the reducing partial pressure of inert gases in the lungs during ascent, the dissolved gas will be diffused back from the bloodstream to the gas in the lungs and exhaled. The reduced gas concentration in the blood has a similar effect when it passes through tissues carrying a higher concentration, and that gas will diffuse back into the bloodstream, reducing the loading of the tissues. As long as this process is gradual, all will go well and the diver will reduce the gas loading by diffusion and perfusion until it eventually restabilizes at the current saturation pressure. The problem arises when the pressure is reduced more quickly than the gas can be removed by this mechanism, and the level of supersaturation rises sufficiently to become unstable. At this point, bubbles may form and grow in the tissues, and may cause damage either by distending the tissue locally, or blocking small blood vessels, shutting off blood supply to the downstream side, and resulting in hypoxia of those tissues. This effect is called decompression sickness or the bends, and must be avoided by reducing the pressure on the body slowly while ascending and allowing the inert gases dissolved in the tissues to be eliminated while still in solution. This process is known as off-gassing, and is done by restricting the ascent rate to one where the level of supersaturation is not sufficient for bubbles to form. This is done by controlling the speed of ascent and making periodic stops to allow gases to be eliminated. The procedure of making stops is called staged decompression, and the stops are called decompression stops. Decompression stops that are not computed as strictly necessary are called safety stops, and reduce the risk of bubble formation further. Dive computers or decompression tables are used to determine a relatively safe ascent profile, but are not completely reliable. There remains a statistical possibility of decompression bubbles forming even when the guidance from tables or computer has been followed exactly. Decompression sickness must be treated as soon as practicable. Definitive treatment is usually recompression in a recompression chamber with hyperbaric oxygen treatment. Exact details will depend on severity and type of symptoms, response to treatment, and the dive history of the casualty. Administering enriched oxygen-breathing gas or pure oxygen to a decompression sickness-stricken diver on the surface is a good form of first aid for decompression sickness, although death or permanent disability may still occur. Nitrogen narcosis. Nitrogen narcosis or inert gas narcosis is a reversible alteration in consciousness producing a state similar to alcohol intoxication in divers who breathe high-pressure gas at depth. The mechanism is similar to that of nitrous oxide, or laughing gas, administered as anesthesia. Being lost can impair judgment and make diving very dangerous. Narcosis starts to affect some divers at 66 feet. At this depth, narcosis manifests itself as a slight giddiness. The effects increase drastically with the increase in depth. Almost all divers are able to notice the effects by 132 feet. At these depths divers may feel euphoria, anxiety, loss of coordination and lack of concentration. At extreme depths, hallucinogenic reaction and tunnel vision can occur. Jacques Cousteau famously described it as the rapture of the deep. Nitrogen narcosis occurs quickly and the symptoms typically disappear during the ascent, so that divers often fail to realize they were ever affected. It affects individual divers at varying depths and conditions, and can even vary from dive to dive under identical conditions. However, diving with Trimix or Heliox dramatically reduces the effects of inert gas narcosis. Oxygen toxicity. Oxygen toxicity occurs when oxygen in the body exceeds a safe partial pressure. In extreme cases it affects the central nervous system and causes a seizure, which can result in the diver spitting out their regulator and drowning. While the exact limit is idiomatic, it is generally recognized that oxygen toxicity is preventable if one never exceeds an oxygen partial pressure of 1.4 bar. For deep dives generally past 180 feet, divers use hypoxic blends containing a lower percentage of oxygen than atmospheric air. For more information, see oxygen toxicity. Hazards due to failure of diving equipment. Hazards of the diving environment. Loss of body heat. Water conducts heat from the diver 25 times better than air, which can lead to hypothermia even in mild water temperatures. Symptoms of hypothermia include impaired judgment and dexterity, which can quickly become deadly in an aquatic environment. In all but the warmest waters, divers need the thermal insulation provided by wetsuits or dry suits. In the case of a wetsuit, the suit is designed to minimize heat loss. Wetsuits are usually made of neoprene that has small closed gas cells, generally nitrogen, trapped in it during the manufacturing process. The poor thermal conductivity of this expanded cell neoprene means that wetsuits reduce loss of body heat by conduction to the surrounding water. The neoprene, and to a larger extent the nitrogen gas, in this case acts as an insulator. The effectiveness of the insulation is reduced when the suit is compressed due to depth, as the nitrogen-filled bubbles are then smaller and conduct heat better. The second way in which wetsuits reduce heat loss is to trap a thin layer of water between the diver's skin and the insulating suit itself. Body heat then heats the trapped water. Provided the wetsuit is reasonably well sealed at all openings, this reduces flow of cold water over the surface of the skin, and thereby reduces loss of body heat by convection, which helps keep the diver warm. In the case of a dry suit, it does exactly what the name implies, keeps a diver dry. The suit is waterproof and sealed so that frigid water cannot penetrate the suit. Dry suit undergarments are usually worn under a dry suit to keep a layer of air inside the suit for better thermal insulation. Some divers carry an extra gas bottle dedicated to filling the dry suit. Usually this bottle contains argon gas, because of its better insulation as compared with air. Dry suits should not be inflated with gases containing helium as it is a good thermal conductor. Dry suits fall into two main categories, neoprene and membrane. Both systems have their good and bad points but generally their thermal properties can be reduced to membrane or shell dry suits, usually a trilaminate construction. Owing to the thinness of the material, these require an undersuit, usually of high insulation value if diving in cooler water. Neoprene dry suits, a similar construction to wetsuits. These are often considerably thicker and have sufficient insulation to allow a lighter weight undersuit. However, on deeper dives the neoprene can compress to as little as 2 and thus losing a proportion of its insulation. Compressed or crushed neoprene may also be used, which avoids the variation of insulating properties with depth. These dry suits function more like a membrane suit. Injuries due to contact with the solid surroundings. Diving suits also help prevent the diver's skin being damaged by rough or sharp underwater objects, marine animals, coral, or metal debris commonly found on shipwrecks. Hazards of marine animals. Hazards inherent in the diver, pre-existing physiological and psychological conditions in the diver. Diver behavior and competence. Inadequate learning or practice of critical safety skills may result in the inability to deal with minor incidents, which consequently may develop into major incidents. Overconfidence can result in diving in conditions beyond the diver's competence, with high risk of accident due to inability to deal with known environmental hazards. Inadequate strength or fitness for the conditions can result in inability to compensate for difficult conditions even though the diver may be well versed at the required skills, and could lead to overexertion, overtiredness, stress injuries or exhaustion. Peer pressure can cause a diver to dive in conditions where they may be unable to deal with reasonably predictable incidents. Diving with an incompetent buddy can result in injury or death while attempting to deal with a problem caused by the buddy. Overweighting can cause difficulty in neutralizing and controlling buoyancy, and this can lead to uncontrolled descent, inability to establish neutral buoyancy, inefficient swimming, high gas consumption, poor trim, kicking up silt, difficulty in ascent and inability to control depth accurately for decompression. Underweighting can cause difficulty in neutralizing and controlling buoyancy, and consequent inability to achieve neutral buoyancy, particularly at decompression stops. Diving under the influence of drugs or alcohol, or with a hangover may result in inappropriate or delayed response to contingencies, reduced ability to deal timelessly with problems, leading to greater risk of developing into an accident, increased risk of hypothermia and increased risk of decompression sickness. Use of inappropriate equipment and/or configuration can lead to a whole range of complications, depending on the details. Hazards of the dive task and special equipment. Scuba diver training and certification. Recreational scuba diving does not have a centralized certifying or regulatory agency, and is mostly self-regulated. There are, however, several large diving organizations that train and certify divers and dive instructors, and many diving-related sales and rental outlets require proof of diver certification from one of these organizations prior to selling or renting certain diving products or services. Underwater diver training is normally given by a qualified instructor who is a member of one of many diving training agencies or is registered with a government agency. Basic diver training entails the learning of skills required for the safe conduct of activities in an underwater environment, and includes procedures and skills for the use of diving equipment, safety, emergency self-help and rescue procedures, dive planning, and use of dive tables. Some of the skills which an entry-level diver will normally learn include, preparing and dressing in the diving suit, assembly and pre-dive testing of the scuba set. Entries and exits, breathing from the demand valve, recovering and clearing the demand valve. Clearing water from the mask. Buoyancy control using weights and buoyancy compensator, finning techniques, underwater mobility and maneuvering. Making safe and controlled descents and ascents. Equalization of the ears and other air spaces. Assisting another diver by providing air from one's own supply, or receiving air supplied by another diver. How to return to the surface without injury in the event of a breathing supply interruption. Use of bailout systems. Diving signals used to communicate underwater. Professional divers will also learn other methods of communication. Dive management skills such as monitoring depth and time and the breathing gas supply, buddy diving procedures. Some knowledge of physiology and the physics of diving is considered necessary by most diver certification agencies, as the diving environment is alien and relatively hostile to humans. A physics and physiology knowledge required is fairly basic, and helps the diver to understand the effects of the diving environment so that informed acceptance of the associated risks is possible. A physics mostly relates to gases under pressure, buoyancy, heat loss, and light underwater. The physiology relates the physics to the effects on the human body, to provide a basic understanding of the causes and risks of barotrauma, decompression sickness, gas toxicity, hypothermia, drowning and sensory variations. More advanced training often involves first aid and rescue skills, skills related to specialized diving equipment, and underwater work skills. Endurance records. The current record for the longest continuous submergence using scuba gear was set by Mike Stevens of Birmingham, UK at the National Exhibition Centre, Birmingham, UK during the annual National Boat, Caravan and Leisure Show between February 14 and February 23, 1986. Mike Stevens was continuously submerged for 212.5 hours, beating his own previous record of 121.5 hours. The record was ratified by the Guinness Book of Records. Mike used a standard regulator and mask and wore only a t-shirt and swim shorts and an 8-pound weight belt. He had no surface breaks during the 212.5 hours. A team of divers attended Mike throughout the dive. The team was led by Diving Officer Trevor Parks. The dive raised £10,000 for the Birmingham Children's Hospital from donations by the public. See also. References. Further reading, Cousteau J. Y. Le Monde du Silence, translated as The Silent World, Hamish Hamilton Limited, London. The Scene B0100 Cuba K890, LBD The Diving Manual, British Sub-Aqua Club. ISBN 0-9538919-2-5, Dive Leading, BSAC. ISBN 0-9538919-4-1, The Club 1953 BSAC. ISBN 0-9538919-5X Richardson D. Open Water Diver Manual, PADI. The Scene B004JZY00E, Free Scuba Textbook by George D. Gamble, 3 called Diving with Deep 6, external links, Divers Alert Network Diving Emergencies Hyperbaric Chamber Assistance, Scuba Diving Travel Guide from Waikiki Voyage.